Hello everyone, my name is Victor Acha and I'm going to be showing you how to do feature engineering using PCA and factor analysis. So let's get into it. Share my screen. Yes, so the title of my presentation is Unveiling Latent Variables, PCA and Factor Analysis of Feature Engineering. So first off, what are latent variables? Latent variables are hidden variables that cannot be directly observed but are inferred from other observable variables. So these are variables that are measured directly, uh, indirectly observed in the data set. So it means that these variables are hidden, sort of latent, and you have to do some sort of transformation, some sort of revealing to bring these variables out. So I say when critically analyzed, latent variables can be used to engineer features in the data that represent the data better than the original features. We all know what PCA is. Basically, it's a dimensionality reduction technique used to simplify complex data sets while retaining as much of the variation as possible. So I say it achieves this by transforming the original variables into a new set of orthogonal variables called principal components, which are linear combination of the original variables. Basically, it does some transformation, takes the most important components uh, and represents it in space. So when obtaining principal components, we multiply the original data by the covariance matrix eigenvectors. Each principal component is a linear combination of the original variable with coefficients given by the corresponding eigenvectors. The eigenvalues represent the amount of variance captured by each principal component. Therefore, selecting the top k eigenvectors and corresponding eigenvalues with the largest eigenvalues allows us to retain most of the variability in the data while reducing its dimensionality. So I won't go deep into it because a lot of us know what this is. So what's the connection between PCA and feature engineering? We introduce the concept of loadings. I say the eigenvalues rather indicate the amount of variance that each principal component captures. So by selecting the k eigenvalues with the largest eigenvalue, k eigenvectors, sorry, with the largest eigenvalues, their corresponding eigenvalues, we can keep most of the data's variability intact while reducing its dimensionality. Now, the thing is that while we're doing this, we can see the loadings. And the loadings represents the elements of the eigenvectors corresponding to each principal component. So each eigenvector represents a direction in the original feature space, and the elements, which are the loadings, indicate the contribution of each original variable to that direction, to that principal component. So knowing this, we can infer that several variables come together in a particular direction, and the most important variables in a particular direction, that is the combination of the loadings, reveal a hidden nature of variable that we could not see. So basically what we're saying is that a combination of variables come together in a particular direction, which are the eigenvectors, right? And as a result, this creates a new characteristics of this or reveal rather a hidden characteristics of the variables that we did not see because now it's in a different direction. It now reveals a hidden nature. Basically, that's what we're saying. Now, the variables with high loadings, positive or negative, are considered more important in defining the direction of a principal component, and therefore the overall character of that component creates the features. Yeah. So what then is factor analysis? So factor analysis basically, okay. Sorry about that. So we'll continue. So into factor analysis. So what is factor analysis? Factor analysis basically is a valuable tool for uncovering underlying structure uh, of a data set by identifying latent factors that explain patterns of the correlations among observed variables. Basically, I would say factor analysis is an easier way for us to read and explain the loadings, the PCA loadings, for a better understanding of the principal components and latent variables for feature engineering. That's my own understanding of factor analysis. So when you do a PCA and you get the PCA components, sometimes it's difficult to read. Now, for you to really understand what the PCA is saying, you do a factor analysis, what the loadings are saying. That's an easier way to understand the loadings and then use it for factor analysis. So steps to doing a PCA and FA, factor analysis for feature extraction and engineering in Python. So the first thing is for PCA, you import the libraries. Basically, as always, we have to import NumPy as an NP. But then the PCA library is decomposition. So from scikit-learn decomposition, you import PCA. And the next step is to standardize the data. So I use standard scalar. So basically you just standardize the data and then you do an initial PCA. The whole idea is to, when you do an initial PCA on the data, the whole idea is to find the best number of components, just like you find the best number of K when you're doing a KN and all this, or any other sort of classification or clustering. So we find the best number of components that covers, explains as much as the data as possible. And the way we do that is to find it from a script port elbow. Now, after that has been done, we get a number of factors, a number of components rather, at where the elbow, you know, bulges out before the other points get flat. Now we get after we get that, the next thing we do is to do the steps for a factor analysis. Now, the thing is about factor analysis in Python, there's a library for factor analysis in R, but when you're doing factor analysis in Python, it doesn't come pre-installed in scikit. So you have to install factor analyzer, which is the library. So you do pip install factor analyzer, and then from the factor analyzer, you import the factor analyzer. Now, after that, you now perform the factor analysis using the number of components obtained from the elbow of the script plot of the PCA. There's an important thing we need to introduce here called a rotation technique. Basically, what a rotation does is it helps to simplify the interpretation of the factors extracted from the analysis. So I use Varimax rotation, and I recommend it. Varimax is good because it's a type of orthogonal rotation method that aims to maximize the variance of the squared loadings within each factor while minimizing the variance of the loadings across the factor. So basically, it makes the high loadings, high, and then they mix the low loadings, low, so that we can easily see what's happening in each factor or components per se, and then we can, you know, understand it. So in other words, variable rotation results in factor loadings that are as close to 0 or 1 as possible, making the factors easier to interpret. So this is an example of fitting a factor analyzer with 6 components using variable rotation. So after we get the factors, and then we interpret the loadings. Now, the thing is, sometimes if you have domain knowledge of the data of what you're trying to do, it will be easier to interpret the latent variables. But if there's no domain knowledge, you can still interpret the loadings, especially if you do a rotation based on what, you know, based on what the loadings are telling you. So I say next is the scores, and for you to do feature engineering after you found it. So this is the thing, yeah. The factors have loadings, right? The loadings represents the directions of, the combination of directions of the variables in the new feature space. These loadings tell us what the characteristics, reveals the latent variable of each factor. But for us to, after we interpret the loadings and we understand what the latent variables that have been revealed are, we still need to put that in the data set, the new data set. But the new data set has variables that have nothing to do with the loading. So to do that, we need to get the scores. And the scores are a dot product of the original variable in the data set with the factor loadings. So the scores give a representation, right, of the original variables, original data point in the original data set in the new feature space. So it's telling us how each particular data point is affected by the new revealed factor, if you get what I mean, the new engineered factor. So that's why I said that the scores represent the transformed data onto a new feature space. It represents the original data point in the original data set in the new feature space. That is, it represents the original data point position relative to the underlying structure captured by the principal component or latent feature. We'll just get into an example to show you how this is done and this is interpreted. So bring up a notebook that I've done. I'm using the Spotify data set, which is a subset of the data set that we're using for our project to illustrate this. So the first thing I do is to load the data set. Just do some basic uh, data set description, just describe the data set, check for non-availability, basically wrangling, right? So after all of this wrangling, I scale the data because, just do min max scalar because I'm just trying to just basically clean the data set. And after this, we do a correlation, right? Just to see, make sure that they are all numerical variables. And that's an important point. You can't do factor analysis and PCA with categorical variables, but you have to create dummies. With that being said, we go straight to the factor analysis. So this is what I said about, importing the libraries. So I imported processing standard scalar from scikit-learn processing, import PCA from the composition in scikit-learn, and then I've already installed factor analyzer. But if I hadn't installed factor analyzer, I'll have to install it. But here, basically, I am I'm just calling up the library from Factor Analyzer. So straight to the PCA, right? Um, I put the data set into a new data set variable just for convenience sake, and for and for just to be careful, basically, just in case I needed this data set. I wanted to just keep the original data set and then scale the XPC. So um, I scaled it, X scaled, and then I did an original PCA fit scaled. Do a script plot, you know, um, and then this. Now, this data looks a bit funny. There are several places that we can pick an elbow, but when it comes down to it, what I usually do is to pick a point that explains as much as the data as possible. So it explains a point where the cumulative explains variance ratio is the highest. So here I pick 6 because I think when I picked 4, let's see if we pick 4, what happens when we pick 4? Um, see, 4 gives us 58%. Yes, but we can also go here and pick and say this could be the elbow because, all of this go down from here. So if we pick 6, 6 explains higher. So let's say I pick 6. 6 gives us 72%. So I print the PCA components. Yes. And then I use 6 as the number of components for the factor analysis. So I picked FA, factor analyzer, number of components, and I do the rotation. This is the rotation I talked about that helps us explain the loadings easy. So I pick 6 and FA, fit it, and then I get the loadings. Now these are the loadings. You see? These are the loadings of the original dataset. The features of the dataset originally are danceability, energy, key, loudness, mode, speechiness, acousticness, instrumentalness, liveness, valence, tempo, duration, time signature. Now, after I fit the loadings, in explaining the loadings, I try to sort them out. So just so that the positive loadings, are separated from the negative loadings. So I do sorted loadings, sort values by factor. Each individual factor, I just keep sorting them out. So, we could do a for loop, but uh, this, I'm just doing it, make it easier. So here, explaining the loadings. This is how to explain the loadings. So in factor analysis, in explaining loadings of factor analysis, the negative and the positive are like two arms. Negative really doesn't mean negative in the sense of a negative value. It just means a different direction. So we consider it in terms of like one going this direction, positive, and the other going in the other direction. But it doesn't mean that the factors, the loadings rather, do not exist in the factor. So what I mean by that is it doesn't mean that the negative loadings, should be taken as negative per se. They're just loadings in a particular direction that all come together to make up the factors, if you get what I mean. With that being said, let's explain these factors, right? So factor 1 here is a piece of music that has prioritizes energy with the loudest loadings, loudness, danceability, liveness, valence, the time signature, which tells us that it's a song, speechiness, duration, tempo, key, and mode. Basically, one of the things I would advise you to do is to always read the data dictionary to so you understand what each particular feature would mean. I have read this and I understand what each particular feature would mean. So it's easier for me to explain the loadings. On the other hand, it keeps instrumentalness, which is like the a measure of if a track is fully instrumental or not. And acousticness, if a measure of if the track is fully acoustic, like without, without any kind of digital sound done live, the other hand, right? So this particular factor tells us that if we're trying to define the mood of this song, it's a high energy danceable song that is not purely instrumental, that is not calm, and it's not live. So this will represent, from explaining from these loadings, this will represent a high energy, loud, danceable song. So the mood that will come out of this will be a high energy, energetic mood. So I call this high energy pop because it looks like a pop song. Then we want to, this is what I've called this high energy pop because energy is the loud, is the high, it gives the highest loading, followed by loudness, followed by danceability, followed by liveness, valence, speechiness, which talks about, if the presence of voice in the song, duration. I should have actually taken out time signature from the data set when I was removing values, but features, but that's all right. E key represents the key that it was made on the song, and then it tells us that, oh, the key that the song is played is quite important, but perhaps not as important as these other features. And then mode represents if and says if it was played on a major or a minor key. And so if a song was played on a major or minor key and a factor, and and this loading is represented, this feature is important, then it all together it represents, it's trying to say that. So if you know anything about um, music theory, music rather, major keys are happy songs. Happy songs are usually played on major keys, and sad songs are usually played on minor keys. So with that being said, this loading explains, in my own opinion, explains a high energy, loud, danceable, positive song. So it represents a high energy, danceable, positive mood. Factor two will represent factor two, see? So after factor two is sorted, danceability is the most important feature. Um, I would say we'll forget about time signature because uh, time signature is supposed to go from 1 to, like 8 or so, but because we scaled it, we should have removed it from here. But with that being said, it's saying danceability is the most important feature, followed by the valence, the loudness of the song, followed by the positivity of the song, followed by the speechiness. So it has heavy voice in it, followed by the key of the song in sense of importance. So, and then the tempo, the beats of the song. This will represent, in my opinion, a danceable, you know, positive, motivational track, almost like the first. And then on the other hand, it keeps mode, you know. So it's saying it's separating the danceability from the key of the song, which it doesn't put as very important. The duration of the song, which it doesn't put as very important. The energy that it projects, it doesn't put as very important. The acousticness, It doesn't put that very important. The liveness and instrumentalness. So this is saying that this represents a danceable, positive, loud, um, you know, and quite talkative mood. And if we think of a song like that, it probably represents a rap song or something that will just motivate you to dance when you speak. So I call it danceable and loud. Factor three. Factor three prioritizes pitchiness, liveness, energy, loudness, danceability, and tempo. And all, almost like just small variations from the first two factors. And then it keeps mode, key, valence on the other hand, and all. So explaining this, I call it just basically um, this might represent, you know, a very loud, voice heavy tune. So maybe like metal, rock, all the songs where you shout, ah, and the rest of them. And then the beats and it's danceable. So, however, this also represents some sort of energy, high energy. So let's call this um, high speechy energy. Oh. So basically, you get the point. This is how to read the loadings. Now, this data set might not be the best data set because the way we pulled it from the API, we pulled albums instead of random songs. Well, like I said, there's a subset of our data, and we're going to get individual songs that will probably randomize and tell us, just explain the nuances in the loadings better. So after you get all of these factors, this is how we do feature engineering. Now, from each particular, instead of having each particular feature, I've had a combination of features in each factor, and each combination of feature represents a new feature. This is how I've engineered features, a new feature, a new feature, a new feature. With that being said, um, I get the features, put them together, and concatenate them with the new data set. And then voila, these are the scores. Remember when I talked about the scores and then the scores representing, each particular point in the new feature space relative to the data set and relative to the um, new feature that's engineered. Each of these represent this scores. So here represents this data point in this new feature space. Here presents this data point in this new feature space. Latent 2, factor 2, latent factor 3, blah, blah, blah. And after that, we can then decide to rename these latent factors with these new features. And that's how to do feature engineering with PCA and factor analysis. In my experience, this is a very good way to reveal latent features in the variables to do a classification, a prediction, and it is very good. I used it first in an MBA data set and it was awesome. Thank you. And that's all.